One thing that separates gases from liquids and solids is the fact that gases have extremely low densities, meaning the particles are extremely far apart compared to the particles in a solid or a liquid. And we can actually use the ideal gas law to determine the density of a gas. Let's first look at the units for density. Density is mass over volume. And we're used to calculating density using grams over cubic centimeters or grams over milliliters. But when it comes to a gas, the unit grams per liter are often used. Now, some things we need to know. We need to know the mass of the gas in question. So we would measure that in grams. We also need to know the number of moles in the gas. So we can use this number of moles, and this would be represented by N in the ideal gas equation. We need to know the temperature of the gas. We would most likely measure that temperature in degrees Celsius, but then convert to kelvins. And we need to know the pressure of the gas. And we would measure this or measure it in a unit and then convert it to atmospheres. So ultimately what we don't know is the volume. If you did know the volume of the gas, finding the density would be extremely easy because you would take the mass over the volume. But if you don't know the volume, you can rearrange the ideal gas law to solve for V, nRT over P. That will give us a certain number of liters, which we can plug into that density formula with the given mass and calculate for the density of that gas. So let's try a question here. How does warm air differ from cooler air? So we're going to assume we have a sample of nitrogen, which is what air is mostly made of. And this nitrogen is at 0.913 atmospheres. We are going to figure out its density. Now the problem is this question is missing some information. nRT over P is what we need to fill in, but we don't know the mass and we don't know the number of moles. Now the great thing about density is it's an intrinsic property. What this means is it doesn't matter how much you have, the density will be the same. If I have a gallon of water, it will have the same density as 5 gallons of water. So it doesn't matter how much you have. So what do you do when it doesn't matter how much you have? Well, you just make up a number. I'm going to choose 1 mole because that's the easiest. And 1 mole of N2 has a mass of 14 plus 14, or 28 grams. So now I can start plugging things into this formula. The number of moles is 1. The R is equal to 0.0821 liter atmospheres over mole K. The temperature. Now this temperature is in degrees Celsius, so we have 20 degrees Celsius. And we need to convert that to kelvins, so we're going to take 273 plus 20. That will give us 293 kelvins. Put all of this over the pressure, which is 0.913 atmospheres. We're going to type all of this into a calculator here. We have 0.0821 times 293 divided by 0.913, and I get 26.35. We'll go 26.3, and that unit is liters. So now I can calculate my density. And because I'm going to be doing some comparing later, I want to be very specific about which density I'm calculating. So I'm going to put 20 degrees Celsius as a subscript. The density of this gas at 20 degrees Celsius is 28 grams over 26.3 liters, which gives me about 1.07 grams per liter. I would probably round this to 1.1 grams per liter. Now the density of this gas at 80 degrees Celsius is going to be different. So we need to plug in a new number here. So we'll take 273 plus 80 to find out our new temperature in kelvins, which is 353. And I'm going to erase that 293 that was originally in our problem. And I'm going to substitute in the new temperature. So instead of the 293, I'm going to put in 353 kelvins. And that's also going to change my volume, so 353 kelvins. So typing this into the calculator again, I have 0.0821 times 353 divided by 0.913. I get 31.74, so I'm going to round to 31.7, and that's my new volume. So I get 28 grams over 31.7 liters, which gives me 0.882 grams per liter. Now I'm going to take both of these numbers and convert them down to two significant figures because I only used 28 as my measurement for the mass of the nitrogen, so I had two significant figures there. So 1.1 to 0.88. What this tells me is hot air is less dense than cold air, which is the reason why hot air balloons are able to float, because they're less dense than the colder air around them.